Hello everyone, I am Fatih Serttas from the Electrical Engineering Department at Afyonkarahisar University in Turkey. Voltage quality is a critical challenge in modern distribution systems, especially under increasing load variability and renewable integration. In this video, I will introduce our work titled Residual-Driven Voltage Forecasting and Power Quality State Classification in Distribution Systems, which proposes a data-driven early warning approach based on deep learning. This study proposes a hybrid deep learning framework called Deep Fusion VS for voltage forecasting and power quality state classification in real-world distribution systems. Transforming power quality monitoring. Modern distribution systems are becoming increasingly complex due to renewable integration and distributed generation. Traditional static threshold monitoring is reactive and often fails to distinguish harmless fluctuations from critical voltage sag events. Deep Fusion VS addresses this gap using a two-stage approach. First, forecasting the expected voltage behavior, and then classifying system states based on prediction residuals. The framework is validated using real hourly field data from 5 substations. With the integration of electric vehicles and renewable energy sources, voltage variability has significantly increased in distribution grids. Voltage sag, as defined by IEEE standard 1159, is one of the most critical power quality problems due to its impact on sensitive loads. In real world, noisy data distinguishing true sag events from temporary disturbances remains a major challenge. Traditional threshold-based approaches rely on fixed limits and lack contextual understanding. Pure forecasting models can predict voltage values, but they do not inherently assess system health or operational risk. Deep Fusion VS bridges this gap by unifying forecasting with classification, where prediction errors themselves become the primary signal for anomaly detection. The proposed architecture consists of two main stages. In the first stage, a CNN LSTM model forecasts the mean phase voltage using real measurements. In the second stage, residuals between measured and predicted voltage are analyzed together with statistical features to classify the system state as normal, fluctuating, or sag. This structure enables both predictive and diagnostic assessment of voltage quality. The dataset was obtained from Osman Gazi Electricity Distribution Corporation in Turkey. It includes hourly active power and three-phase voltage measurements from 5 substations with diverse load characteristics. The dataset spans tens of thousands of data points, enabling both long-term trend analysis and rare event detection. Daily voltage profiles reveal clear load-dependent behavior, with voltage drops occurring during peak consumption hours. The anatomy of a sag event shows sustained voltage reduction below 9.90 per unit, lasting several hours. These characteristics motivate the need for time-aware and residual-sensitive analysis rather than instantaneous threshold checks. The CNN LSTM model consistently outperforms the standard LSTM across multiple substations. In high variance nodes, where standard LSTM fails, convolutional layers significantly improve prediction accuracy. This demonstrates the ability of CNN LSTM to filter noise and capture complex grid dynamics. Time series comparisons show close alignment between actual and predicted voltage values. Bland-Altman analysis confirms that residuals are zero-centered and free of systematic bias. This makes residuals a reliable and informative signal for downstream classification. Voltage states are classified using a 12-hour sliding window approach. Normal states exhibit stable voltage and low residual variance. Fluctuating states show increased variance without threshold violation. Seg states are characterized by voltage drops below 0.9 per unit or strong negative residuals, indicating critical conditions. The proposed model achieves an overall classification accuracy of 83.2%. Normal and fluctuating states are identified with high reliability. Most importantly, seg events are detected with high recall, minimizing the risk of missing critical faults. Voltage seg events are rare but safety critical, leading to severe class imbalance. In power system protection, false negatives are more costly than false positives. Therefore, the model is intentionally tuned to prioritize recall over precision. Model performance varies across substations due to different load characteristics. Industrial feeders exhibit higher randomness and lower forecasting accuracy. However, residual-based classification remains robust, demonstrating that fault signatures persist even under systematic bias. This highlights the limitation of one-size-fits-all models in real grids. Diffusion VS provides a robust and scalable framework for voltage quality intelligence. CNN LSTM improves forecasting accuracy under real-world noise conditions. Residual-based analysis enables reliable detection of rare but critical seg events. The framework is validated on real distribution data, not laboratory simulations. Future work focuses on online deployment in SCADA-based early warning system. This study is based on IEEE power quality standards and validated using real data provided by OEDASH. Thank you very much for watching my video.